let's talk about the first and second derivative tests. So recall that these tests are designed to determine the local extrema behavior of a given function. Okay, we're looking for the actual behavior of the original function. So recall that the first derivative test is a test that is designed to determine whether or not you have a local minimum or a local maximum value. The first step in the first derivative test is to find the critical values of a function. Remember that critical values occur at two locations. They're places where either the derivative is equal to 0, so in order to find the critical value, we solve this equation, f derivative at x is equal to 0 for x. That'll give me all the x values for which the derivative is 0, or where the function is transitioning from going up to going down. Or they're places where the derivative does not exist. Remember, it's possible that we have some kind of sharp corner, either sharp corner up or sharp corner down, where the function does not exist, and that could be the location of a local minimum or a local maximum. Usually what we do is we look at the original function and sort of determine what values it may have. In other words, whether or not the derivative, or I should say the original function, is differentiable everywhere or not. And we can look for those values just by looking at the original function. Okay, so that's the first step, is to determine where the critical values are. These are places in the domain, they're x values, where the function has some kind of critical behavior. It does something. Either it's increasing and then decreasing, decreasing then increasing, or it has a sharp corner somewhere. Okay? Or neither, depending on how the function behaves. But that's why we have to go through the second part of the first derivative test. That is, we actually have to test the values. Remember also that the derivative, the first derivative of a function, gives us information about whether the function is increasing or decreasing. Recall that if the derivative of a function is positive, that means the function is increasing on that domain, or for that x value. That's because the tangent lines to the function at that point are positive, which means the function is increasing. And similarly, if the derivative of the function is negative, that means that the function is decreasing for that particular x value. And the nice thing about the first derivative test is that we can find out the behavior, whether increasing or decreasing, for all x values for a particular interval, because we know that the critical behavior only occurs at the critical values of the function. Okay, and that's the power and beauty of the first derivative test. It gives us all the information we need to know, all in one shot. Okay? And remember that in order to actually apply the first derivative test, we first of all find the critical values. Let's say we have C1 and C2 are our critical values. And then what we do is we take those values and we want to know what is the sign of the derivative as a function before and after these critical values. Because we know these are places, or at least candidate places, for which the function may have a maximum or a minimum locally. But we need to determine what they are, whether they're really maximum or minimum. Okay? To do that, remember that what we do is we take values, that is x values in the domain, and usually we write a number line here to get a graphical representation of what's going on here. We take these x values before this critical value C1, put it into the derivative function. We find out whether the sign of this is positive or negative. We put that down here. Let's say it's positive for all x values before C1. That means that the original function, if I write down f, is definitely increasing for that domain, that part of the domain. If the sign of the derivative is negative for all x values between C1 and C2, and it'll behave the same way for all x values, because these are critical values. That's a nice thing, again, of the first derivative test. Then I know the function is decreasing everywhere, for every single x value between C1 and C2. However, if I take x values after C2, and let's say that I get another negative sign, that is that the second derivative has a negative value after this C2, that means the function is still decreasing here. And in this case, we get sort of, in some sense, these points have failed the first derivative test, meaning that this is definitely a critical value, but it's not going to be the location of a local minimum or a local maximum. Okay, the function's still decreasing. And that's why, even though we've found the critical values, we still need to go through the first derivative test, that is, finding out the sign of the first derivative, in order to determine whether or not these critical values really are local minimums or local maximums. Okay, so the first derivative test includes not only finding the critical values of the function for its particular domain, but also looking to find out, to test the sign of the first derivative for all of these portions of the domain. So notice also that what we've done when we compute where the critical values are, we're essentially breaking up the domain of the function into different chunks, right? We are partitioning the domain, and we want to know whether the function's increasing or decreasing on those portions of the domain, okay? Let's talk next about the second derivative, and then we'll do an example of using the first and second derivative tests.